Hi, everybody. Today, we have a guest to give us lectures on the relationship between mathematics and the work that he's currently doing. So, our guest lecture today is Keith. He just like you guys, he has a bachelor. He's in computer science, and he got his bachelor in 2017. So when deciding the guest lectures for these modules, right, we decided to get someone who has just, been working not for too long, so that it's more relevant to you. As you guys knows that computer science or technology is very fast paced, so it is kind of quite not that relevant to get someone who worked for 20 years. He might be doing things that is not that similar to what you guys will be doing when you graduate. So that's why we want to get someone who has been in the area, relevant area, so that he can give you a relevant insights and what kind of jobs that you'll be doing next time. So we are very fortunate to have Keith to come here and share with us his experience in working as a back-end software engineer and more relevant in the area of deep learning. So Keith is an expert in the area of AI, machine learning, and deep learning. So I got to know Keith because of my previous job in ST engineering, whereby we were involved in the data science consortium, and he was one of the key players in developing machine learning and AI solutions for our company. So AI and machine learning is pretty wide. So his main domain expertise is actually in video analytics. So if you notice, right, for video analytics, there are many use cases. For example, one of the major use cases for his expertise will be in people counting. So you will have a automatic people counting in video analytics that's count the number of people in real time and can update the control center on how crowded that particular place is. And in addition, he has also developed video analytics for car plate recognitions. As we understand, in Singapore, all the cars has ERP, so it's not that. So this particular car plate recognition is mostly deployed in other countries whereby they don't have ERP system and you want to track the vehicles on the road. And so all these are his working expertise. And in his spare time, he is an audiovisual artist. So and his keen interest is also in video jokering. So if you want to know more about his hobby and spare time, well, you can speak to him and chat with him later. So without further ado, I will stop share now and pass the time to Keith. Keith, thank you.
Hey, thank you, Kapil. Yeah, so thanks for the introduction and thanks for inviting me over. Can everyone see my screen? Just show a thumbs up if you can. Yeah, I think there's an additional thing I need to do. Okay. Yeah, yeah, thanks for having me. And for the next 1 hour, I'll be sharing with you guys a bit about, modeling the continuous world. So the world we live in is a continuous world, and we can describe it in continuous math. But sometimes when we are using computer science, right, we have to use discrete math to describe the real world and model the real world, right? So there are some disadvantages to this. There are some advantages to this. So I just want to bring you guys through like what are some of these things that we face in computer science, and of course in deep learning that I'm working on previously in my job as well. Yeah. So if you guys have any questions or anything, just drop them in the chat, right? We'll have a Q&A session at the end also for about 15 minutes where I will, cover some of the questions that you guys have if I can answer. So I'm quite junior as well. I'm not someone who knows everything, but I think, in terms of, let's say, career or in terms of what kind of work I do or even some technical questions, I hope I can answer them. Yeah. So yeah, as Kapil said, like who I am, I actually graduated very recently, only 2017. And yeah, I'm a deep learning engineer, backend engineer. and interested in audiovisual arts. So I also cover some of these things that how audiovisual art in the modern context, right? Is making use of a lot of these computer science things and a lot of things that we have to also take note of when for example when we are listening to music, when we are playing games, when we are watching videos. So I'll make it a little bit more relatable to you guys instead of just going to how we um you know in my job actually do things like reading license plates for some other country which might not be that relevant to you guys, right? So the first thing I want to show you guys is this map of mathematics that I actually got from one YouTuber, right? His name is Dominic Wallyman. Below, you can actually search him up, and on YouTube you can search the map of mathematics to get this whole map of all the different areas of mathematics. It's very big, right? Like there are people who are doing over here biomathematics, mathematics in chemistry, right, which I'm sure some of you might have touched in secondary school, mathematical physics. All these are the applied maths that we are more the math that we are more familiar with when we are doing physics. And then areas such as finance, when we model uh, the financial world and economics using mathematics. Statistics, there's definitely some parts of statistics that you have learned before. The probability of something happening, the probability of something happening when something else has happened, stuff like that, right? And when we move up here, maybe in the future, I'm not sure whether you guys have learned already in cryptography, right? Even in crypto blockchain, for example, even using your Wi-Fi these days, right? There's a password, and then there is cryptography that's happening behind the scenes that you guys are making use of every day, right? Computer science, machine learning, which I touched a little bit on, optimization, to find what is the most optimal way of doing certain things, right? Multivariable kind of optimization where we are using where we need to find the most optimal out of many different possibilities, right? There's so many other things as well in the pure mathematics side of things. And pure mathematics, a lot of it starts out as very in a very abstract way of thinking, and then over time maybe some of these things are actually used in the real world in applied mathematics. So in computer science especially, we see a lot of these things happening, right? Like set theory, using trees to represent data structures, using graphs to represent things like maps, or graphs to represent things like social networks, right? How to find who you are most close with, or who is the second closest person, so that you can actually find the related friends of some person, right? Number theory is also used a lot in computer science, and of course in linear algebra when you are doing machine learning. A lot of this linear algebra is being used. Matrix multiplication, not sure whether you guys have touched on it before, but we are matrix multiplication, matrix addition, stuff like that. We use a lot in machine learning. Yeah. So yeah, I will not cover the rest. It's a very nice video. So if you guys want to search it up, I will probably link it to you guys later on. It's like a 10 minutes video where he goes through all these parts of it, right? So um what we want to touch on today is more of like the incompatibility between the continuous math that you always learn in school, and previously in secondary school, and computer science, how that's a little bit of a mismatch, and we kind of have to use discrete math to represent what we see in the real world, right? So for example, the first question is, how do you represent 1/3, right, in base 2? Not sure whether you guys know what's base 2, right? So base 2 is basically when we use computer science, right? There's only just an on and off state for the transistors, and then we have to represent numbers, we have to represent commands and all that in base 2 in just zeros and ones, instead of having 0 all the way to 9 to represent numbers, right? So yeah, the way to represent 1/3 in base 2 turns out it's actually 0.010101, and it goes all the way on. And you can kind of understand this also when you are using, when you try to represent 1/3 in base 10, right? Which is the typical way we represent numbers, which is 0.33333, and it's all the way on. So there's not really a way where we can represent this kind of numbers in base 2 or base 10. But we have to find a way. If not, like how would the physicists or the scientists use computers to do their large amounts of computations, right? So yeah, just a short primer on base 2, right? In case you guys are not familiar with. So you can see for the number 0, right, in normal base 10, we represent it as 0. For the number 1, we represent it as 1. For the number 2, for example, we will actually uh, jump one number, right? So we will carry over the number from 0, from 0 to 1, the second digit, and then the first digit we change it back to 0. So it's the same as, for example, you have 0 to 9, and then after when you want to go to 10, right, you make the second digit 1 and the first digit will be 0 again, right? So the problem with this thing is, I mean, one of the problems you see, right, is that when you reach a number like 4 or 5, right, you actually need 3 digits just to represent this number 5. So you can think of it like in the computer world where like you have transistors or registers to represent all these numbers inside the CPU, right? It will actually require 3 of these things just to represent the number 5, right? And then what if we want to represent a big number, right? Like 65,000, for example. You end up having something like this, which is 16 digits just to represent this number, right? And what about small numbers, right? This comes the problem, like it's very hard to represent small numbers. Yeah. So we actually came out with a system. I mean, not me, but like the the engineers years ago, in IEEE, right? They came out with this system where you can use 16 bits of number to represent very small numbers and very large numbers, right? So there are 3 parts to this. There's the exponent, and then there's the mantissa. So what we do is actually we just multiply them together in a certain manner, right? So for example, over here, you see that in the green part, right, you see that the exponent, we are just using 2 to the power of the exponent minus 15. So in this example, the 2 is a 1, and the 16 is a 1. So we take 16 plus 2, and then we minus 15. So this is, uh, a high power. And then the mantissa is a fraction, right? So you take 1 plus, in this case, we have 4 plus 2 over 1024, right? So with this, we can actually represent a number like 8 point something, 8.046, blah, 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 right? And then if we want to add a certain small number, if you want to have a small jump, right, you just add a number into the mantissa, right? You just add 1 to the 1 here, and you can add a small number. If you want to have a big jump, you can actually do like increase the exponent a lot, right? Which will just increase the power, which will increase the whole number by a lot. And then the sign will just help you do the negative side and the positive side. So you see, with this system, we can actually represent a whole range of numbers from small to big, right? The largest positive number you can actually do here, right, is actually to take this exponent, change all the way to 30 minus 15. And then this mantissa, you add all of them to be ones, right? And then you get 1024, right? So yeah, you get a very large number, and the smallest number is this, when you get everything to be 0, and then the mantissa to be a very small number like 1, right? Then you get like 5.9 to the power of minus 8, which is very, very small. So with this, we actually help the scientists and the engineers solve the problem, right, of having very small numbers and very large numbers all in a very easy way, a very small 16 digit number, right? So what are we losing when we do this, right? There can't be any, there can't be like only good things and no bad things, right? So we actually end up losing the ability to represent the numbers in the middle. So you see, if I want to go to 8 point, if for example the number that I showed you just now, 8.046, right? If I want to go up by a little bit, the only number that I can go to is 8.054, right? And this number is, there's a jump, and we can't have numbers like 8.047. We can have numbers like 8.05 exactly, right? We can't have these numbers. So that's the problem with this system that we have, right? There's always a jump, and this is the discretization of in computer science that I'm talking about, rather than the continuous numbers where between every number there's always another number. Between 0.4 and 0.5, there's always a 0.45, and then in between there's even more smaller numbers, right? There isn't this kind of theoretical concepts that we can model inside. Right, so this is a meme I found last time. So if you guys are familiar with like working in float 64, maybe you have done some programming in C++ or something. You see, when you do some kind of multiplication or addition of small numbers, you end up having something like this 0.300004, right? In most cases it's okay, right? If let's say you are a scientist and you are trying to do some of these calculations, you're actually getting you just need to take the three significant figures, and that's what matters, right? In the same way we do it in secondary school. Yeah, but if you come from a pure mathematics kind of standpoint, right, 0.3 is not equals to 0.30004. Yeah, so this is the if let's say you draw it out in a number line, you see you get this kind of problem where like in between numbers you get a certain gap, and actually there are more missing numbers as you increase the exponent, right? So you see over here our exponent is 4, right? For the green dots, the exponent is 4, and then when we move up to the exponent of 5, the numbers actually become spaced further apart, right? So the addition in between is 0.015, but when we jump one exponent, right, from 2 to the power of 4 to 2 to the power of 5, our exponent actually, our difference actually goes up to 0.03, like double. And then this goes even further and further, the bigger of the exponent you use, right? So that's one problem that we have, right? So let me tell you a little bit about how it works with machine learning, image recognition in deep learning, which is what I'm familiar with in my job, right? So deep learning is actually used in a lot of places these days, right? It's not just for like counting people or surveillance state things. It's also used in AR filters that you use every day in Instagram, TikTok, Snapchat, right? All these things have to work using deep learning because they have to find the position of your face in the whole frame, have to find the position of your eyes, nose, mouth, and then overlay this AR filter over it, right? So how it works is actually that the images are not smooth like in the real world, right? You don't kind of describe an image with uh like a million curves with different colors. You would be familiar with like images will have pixels, right? And these pixels, each one contain a number, and maybe each image contain 3 sets of these pixels, right? 3 layers of these pixels, one for red, one for green, one for blue, and then we then add them all up, and your eye see it as something that looks familiar, something that looks like uh, a pic a picture, a real person. But actually, if you zoom in, this is what it looks like, right? And what happens in deep learning is that you see a lot of these operations happen, right, where you take everything that is green, right, which is 1, and you take everything that's orange or yellow, right, and then you do a multiplication and addition, and then you get 4. So you can imagine like if you have one image and then you have these what we call kernels or filters actually going through the whole image, right, many times, right, to get a new image. A new image or a new number here in pink, right? So this is what happens. There are a lot of multiplication and addition that's being done every single time your computer or your phone actually does one of these image recognition tasks, right? So it does this many times, right? I'm giving you a very short overview here just to not go too deep. So it does this many times over multiple layers, right? I would say the number of multiplication tasks that they are doing is in terms of like billions, right? And then at the end of the day, it will determine, whether this number over here, this picture over here, like is it number 2, right, for example, or is it a face, or where is the face, right? Like where is the eyes, where's the nose, where's the mouth, to, for example, overlay the AR filter on it, right? So the problem with this is that, like, deep learning, actually requires a very large range of numbers for better accuracy. So just now I show you a 16-bit number, right? With 16 digits, and you can represent from negative 6,000, 60,000 plus to positive 60,000 plus. But deep learning actually requires more than that, right? It requires you to do more than to the power of 4 or 5, right? So something you can do, over here you see the way that what I was showing you just now, the 16-bit floating number is 65,000. So it's 6.5 to the 10 to the power of 4, right? IEEE actually has another standard called the 32-bit floating point number, right? Which uses even more space, right? It's 32 bits. And then it can go up to the power of 38 actually, which is way more than the power of 4 over here, right? So you get a larger range and a larger precision as well, right? And this actually is how this is actually the floating point number that most people use to do machine learning, to do deep learning, so that they can get very robust models that um, get the result very quickly without having too much training, or like the training would be more successful, right? So the problem with large numbers is this, right? It requires more storage. You can imagine, if you want to store um, a 16-bit number versus a 32-bit number. So you actually have to use double the storage, right? So your machine learning model becomes like double the size. And you can imagine, if let's say you store it in an app, right? Your app becomes double the size. And yeah, you require more storage, more computational power, because when you want to do a multiplication with 32 digits as compared to 16 digits, it's of course going to take longer and more computational power. And when you go to silicon space, when you talk about silicon space, when you have the CPU and it's etched on the silicon in the factories, right, you have to sort of double the space as well, right, so that it can hold the circuits that do all these multiplications, right, of 32-bit numbers. And of course, it draws more power, right? So you can see from the image here, the registers actually double the size. The lanes that, the pipes that connect the CPU to the RAM actually also have to double in size. And the amount of data that's flowing through, every time you pass a bit of data through, it's sort of like you increase the voltage, right? To sort of pass this data from the CPU to the RAM, or the RAM to the CPU. You increase it to 1 or you decrease it back to 0. So this will actually increase the power as well. So our goal is actually, right, we want to have the same range, but we also want to have a larger range, but we want to use the same number of bits, right? So what can we do here? So some of you might have noticed already, we actually increase we can increase the exponent very easily, right? But we have to give up the mantissa, the fraction, the red color part, right? So Google actually invented this a few years ago. I wouldn't call it invention, it's just a new standard, right? Actually, so the green color part, as you can see, the exponent actually increased from 5 bits, right? 1, 2, 3, 4, 5, all the way to 8 bits, right? So that will allow them to go to the power of 38, right? But at the same time, they are giving up the mantissa. So the mantissa from 10, it becomes 7 bits only, right? So we get a large range, but less precision. When I say less precision, what does it mean? It just means that the gaps between numbers get larger. So just now I was showing you the green dots and the orange dots where the gaps have space, right? But now it gets larger, right? So it turns out that people found out that precision is not that important, right, when we are doing deep learning. So that's why we want big range, but precision doesn't have to be that fine. So then comes the question, right? Can we save even more power, even more storage? Because we want it on our phones, right? We want it on our cars. Our cars run on battery. If you, Teslas, for example, run on battery. And if let's say you use too much power in doing all these machine learning things, you get less range for driving, right? We want our phones to last the whole day. We don't want to charge it every 4 hours, right? So we also don't want to, another reason is we don't want it to be, we don't want all this data to be sent back. Let's say you're doing it on videos or audio, right? It's actually a lot of bandwidth, to send back so much pictures, videos, or audio to the servers, to do all these kind of machine learning tasks, right? So another thing is privacy also, right? We don't want um, your Alexa to, for example, keep listening to what you are saying in your house and send it back to Amazon, right? Even Siri, we don't want it to keep listening to what you are saying all the time, right? There's privacy involved as well. That's why we want machine learning to go to the edge, right? We call it the edge devices like your phone. So another thing that has been done, right? Tesla has actually recently released a paper showing how they do it. So they reduce, they have a new format called Tesla C Float 8, right? Um, the short uh it, the short story is this, right? They keep the same number of floating point numbers, right? Sorry, they reduce it by half, so 6-bit becomes 8-bit, right? The exponent stays the same, it's 5 bits, but the mantissa actually reduced very, very drastically, right? From 10 all the way to 2, right? So this gives us a similar range, right? It's also 2 to the power of 15, but it's even less precision. So if you can think about it, the intuition is like this, right? If Instagram doesn't detect your face correctly, right, it's not really an error, right? It's not sometimes you face glitches on the Instagram AR filter where maybe it detects the face of, I don't know, your dog beside you or something like that. But it's not that important, right? As long as most of the time it succeeds, it's good. But let's say you are facing low frame rates on Instagram, or Instagram is sucking your battery power, that's actually a very major problem, right? So this is a trade-off that we are willing to make, right? We want to represent the model, the world in discrete manner, but we want to use as little power as possible. So it is discretization with some kind of trade-off, right? So this is a very nice representation that I saw in uh, uh, NVIDIA, that I got from NVIDIA. So NVIDIA actually touts their Turing tensor core, and these cores, as compared to the old way, they do much faster computation, and these same cores they can actually do it in what they call integer 8 as well, which is the same as similar to floating point 8, right? Similar to Tesla C float 8 in the sense that it uses 8 digits to represent the number as compared to 16 digits. So with that, they're able to do 2 times the computation, right? And NVIDIA is also even talking about integer 4. So instead of using 8 bits of to represent it, they use 4 bits. So they will get even more improvement, right? In the real world, what does it mean, right? In our lives, what does it mean? This means that like when you're using when let's say the people at Facebook, Instagram or Snapchat, they optimize their models, their deep learning models for integer 4. You can actually have a smoother experience when using AR filters. You have smaller power usage when let's say you are plugging your Alexa or Google Home into your home. You don't actually use that much power constantly. So this translates to a lot of savings down the line for us consumers, and more democratization of all these technologies to us. Right, then next area I'll talk about where we face problems that we have to overcome with discretization is in music, right? So I'm not sure whether any of you are audiophiles or you have friends who are audiophiles and they buy a lot of gear. They buy the MP3, not MP3 player, the music player that can play lossless or FLAC kind of formats, right? And then they buy good cables, they buy good headphones, right? And then they want to have these kind of things that they call lossless, and they know things like 24-bit for 44.1 kilohertz, stuff like that. All these tech specs, right? So the thing is, original sound waves in the real world are sort of smooth, right? They're just oscillating atoms or molecules in the air, right? There's no like discretization of it where like a molecule suddenly jumps from one place to another place and one place to another place, like how we have to deal with floating point numbers. But we have to sort of translate that into floating point, right? And one idea that one concept that you have to learn about it is bit depth, right? So in the continuous world, you have a smooth wave, right? But when you uh, move to a CD, for example, which is 16-bit audio, right? There's actually jagged, is more like a jagged wave. And when you go to 24-bit high resolution audio, it's a smoother wave, but if you zoom in, you can actually see that it's jagged, right? Because in 16-bit, just now I show you there's about 65,000 possible numbers, right? Then in 24-bit, when you expand it even further, there's 16 million possible loudness levels, and that's how we try to approximate the real world, and we try to get a better, so-called better quality sound, right? That we cannot distinguish from the real sound, right? So another thing that we have is the sampling frequency, right? So if you look at the picture on the left, right, you can see that if we have equally spaced dots that are very close apart, we can kind of represent this smooth wave, right? Then when we have dots that are further apart, right, we will not be able to actually represent this smooth wave. This very thin wave actually becomes a very large wave, right? Which is not correct, right? Which is not what the wave actually sounds like. Right? So actually, what is the number of dots, or what is the closeness of dots that we require for us to get a good representation of the wave, right? This is something that is called the Nyquist frequency, right? So it turns out that what you need is just uh double the frequency, right, to get this best frequency, because um all you need is a dot at the bottom of the wave, a dot at the top of the wave, a dot at the bottom of the wave again, and then you can actually represent this wave already, right? You don't need to have more, like this picture here, which has so many dots. You don't, and you cannot have less, because there will be the picture below. And since most humans actually only hear up to 22 kilohertz, right? Above that, you are either a dog or a bat or something. Then 44 kilohertz, which is 22 times 2, is technically enough. And which is why every time you look at those um like audio specs, right? If let's say you're into it, you'll see that it's 44.1 kilohertz, right? The most we go is maybe 48 kilohertz, right? And maybe those really audiophile people, they want to have double of that even, which is actually not necessary. I'm not sure how many of you can hear the difference, right? So, but we cannot all have um large audio files, right? Because how many of us want to bring all these huge equipment around? How many The internet cannot be congested with people listening to um audio files that are so large in size. Your Singtel and StarHub would probably not be very happy if, let's say, everyone's just trying to stream the lossless audio at 24-bit audio over their 4G network, right? So what we do this is we actually map it down, right? And we have, like, for example, a 32-bit to 16-bit. So I draw a 16-bit line just now, right? Remember? And let's say we want to move from 32-bit to 16-bit. We actually have to do some kind of things called quantization, right? So there's a few numbers. There are many, many numbers in 32-bit or 24-bit, and we actually have to round it down to one certain number in 16-bit, right? So, I mean, as you can see, this causes problems. It's sort of like taking a smooth wave and making it into a jagged wave, right? There will One way I can kind of represent it for you is, like, for example, a friend owes you $4, right? But he can only return you $0 or $10 because he only has a $10 note, for example, if we're doing it in cash, right? So so if he doesn't return you, right, you're kind of like losing $4, right? Um, yeah, so this is actually something that's being done, 44 kilohertz, which is like 44,000 times per second, whenever you listen to something that has been downsampled, from 24-bit to a 16-bit audio, right? So this is actually orally noticeable, right? Let me share with you guys like an example to show that it's actually visible. Can you guys hear the audio? Just give me a thumbs up if you guys can hear. So this 16-bit, right? If you go to 8-bit, yeah, not sure how many of you can hear. Actually, there's some kind of hissing noise at the back, right? Wait, let me see whether I'm using high quality audio. Yep. Yeah, if I go to 16-bit and 8-bit again, it sounds nice. When I go to 8-bit, yep, there's that soft hum behind, right? Yeah, Kasiak, you said about, yeah. Okay, let me see if I can make it louder, right? 16-bit, and 8-bit. There's this glitchiness. Okay, maybe it's just Zoom also lah. It's Zoom because Zoom also compresses the audio, so maybe it's the Zoom compression as well. So you see, the problem is that you can actually hear some kind of difference in it, right? Okay, so that's caused by the discretization, right, of audio, right? So and one of the ways we can solve it, right, and there's actually a name for it, it's called dithering. And dithering is actually just simply adding noise or randomness to this. Okay, it's not that simple, like, but this is a visual representation of it, right? How you can actually not map everything properly down, like previously, we don't map everything properly down to one value. We actually give it some space uh, and some randomness in how it maps, right? And if we do this, it turns out that we are actually the human ear is actually better at the human ear actually thinks that it sounds nicer, right? So I think this is quite a good example. Let me just um, share it with you guys in the chat if you guys cannot hear it. And next is when we add dithering, right? We add the noise. So there's number one, which is like high quality audio. There's number two, which is low quality audio without dithering. And there's number three, which is low quality audio with dithering, right? Number two is very harsh, right? You might not some of you might prefer it, I don't know, right? Number three is like you can still hear the noise, right? There's noise because we added the noise, right? But the thing is, overall it sounds smoother. And I think if you listen to it a longer audio track or like an audio track that has more things in it, right, your brain actually naturally filters out that noise. And this is a very extreme example. It's all the way to 4-bit, right? The kind of the lowest that we go, maybe it's usually 16-bit or or something like that, or 10-bit, right? But no one goes all the way to 4-bit when you are listening to something on Spotify. But you can get the idea, right? If let's say you are on very good speakers and you hear something that is from 24 bits to 16-bit, you hear this weird noise at the back. But if the sound engineers do it properly, right, you don't hear it. You don't hear it, and you maybe can hear a slight noise, but it goes back after a while. It goes away after a while. So um, you know, the thing I think one thing I want to bring out is that, it's not that always that low quality is bad. It's not that always 8-bit is bad and 16-bit is better and 32-bit is even better and 64-bit is even better. There's in music, and in pictures or things like that, there's always some space for us to actually enjoy the aesthetics of something that is low quality. So there's actually this thing called 8-bit music, right? And this is just one example. Yeah, you guys can listen to more of this. You guys can go to like YouTube or Spotify to search out for this. Like there are whole like artists that are actually base their whole aesthetics around this and then make a lot of 8-bit music, right? Not even 16-bit. Right. So dithering is not just something that is done in music. If end up studying a lot more about signal processing, right? There's actually uh, like a lot of similarities between audio processing and image processing and video processing. And in images, they're doing the same thing as well, right? If you look at the first image on the left, this is the clean, high quality, high storage kind of image. You can go in the middle and you see that this is low. We can call it like a low quality image without any dithering, and on the right is something that is dithered. So if you step back from your screen, right, if you look from it from a further point of view, I think you would think that the right one is smoother, right? Just like how the audio just now, the 4-bit dithered music is smoother as well, right? It's just how our brains work, right? It turns out that we don't like orderly constant errors, and we prefer noise to it, right? And there's actually a whole area of study about this, right? There are so many different algorithms for dithering actually. Yeah. And games and movies, right? I think we're running a bit short of time, so let me just go a bit faster. So some of you might be familiar if you are gamers, about RTX on, RTX off. Not sure how many of you have like the latest NVIDIA, 3080, 3090, where you can use RTX, right? You can see that the water here is a lot. It kind of looks more real because it's reflecting the fire. However, over here it just looks like some painted water. Yeah. And yeah, maybe I'll not show this. I actually had this like Linus Tech Tips video about how ray tracing works, but let me not go through it. I'll just show you guys how ray tracing work in my own manner, right? So how ray tracing work is that, like, you kind of want to represent the real world in by showing how the photons actually move, right? By mimicking how the photons move. Yeah, then yeah, so how it works is that, like, in the real world, for example, the light source is the one that actually take comes out with like billions of photons and then reflects off you and goes, and some of it goes into your eyes, right? Just luckily some of it goes into your eyes, but in your computer you can't really do that. You can't have 10 light sources in your game and then like the computer just um models all of them flying around all the area, because that's too much. So we do the opposite, right? We let the camera or your eye be the one that throws out the rays, right? And when it hits an object, right, we kind of have the the shadow ray that is emitted. So we know what is the angle of incidence, these kind of things that you learn in physics last time. And we just keep repeating this process where it jumps from when it bounces off from one object to another object to another object, all the way until it hits a light source. And if it hits a light source, it means that all the way down that whole ray, right, there's actually light. But if we bounce like maybe 10 times and then we don't see any light source, it means that pixel is black, right? Not sure if you guys catch what I'm trying to say, right? So we do it the opposite way, and this allows us to actually model the real world, right? So but the problem is, right, when we are using floating point, right, how do we actually know that one of these rays have hit an object, right? Because an object could just be very thin, right? It could just be a piece of aluminum foil, for example, that you modeled in your 3D software, right? Uh, yeah, so sometimes the ray never gets to hit the ray, yeah, the ray never gets to hit a light source because your expectation is that this, right, your um ray hits this object and it bounces off. But because of floating point, which I told you is like discrete points, right? You can kind of think of it like that. It actually misses the first, it actually misses the edge, right? And it goes inside. And what it does is that, okay, the ray knows that it has hit the object, because if you pass that object, it means you have hit that object, right? If you have intersected that object, it means that you have hit it. But it tries to bounce out again. But when it bounces out again, right, it actually hits itself. It actually hits the object, the inside of the object, right? Rather than hitting the outside of the object, right? It bounces off inside and it hits the inside of the object again, right? And then now we think that the computer thinks that that ray is actually black because it doesn't hit a light source, right? So it creates a shadow for this new ray. So what this looks like in your when you look at your screen is that that pixel is black, right? It's not supposed to be black because it's supposed to bounce off and hit a light ray, hit a light source, but it doesn't do that. So that's something that happens when you're using floating point numbers, right? Discrete numbers, in fact. So this is what it looks like, right? Some of the poorly implemented ray tracing algorithms, right? Is what it looks like at the left, right? The hack is that we actually add a very small number to prevent this from happening. So instead of saying that like it it will have to, you know it, instead of saying that like it has to hit it exactly and bounce off, we actually give it a range that it can hit and then allow it to bounce off. So we call this very small number the epsilon, right? It's actually a very simple hack that you would find very weird if, let's say, you are doing computer graphics, but this is a way that a lot of it works, right? So with epsilon, it looks like a smooth sphere. Right, so I found this meme that was on Facebook. Yeah, I know I'm old, so I use Facebook. So, uh, you look at this code over here, right? There is just this very random and out of place constant over here that they use, 1 to the power of -3. So this is what we call the epsilon, right? And it's what we use to actually prevent these kind of things from happening when we are working with floating point numbers. So I actually found in the comment section as well that they say that this technique is actually used a lot in astrophysics simulations, right? I think all kinds of physics simulations as well. Yeah, so um yeah, what happens is that they are trying to, instead of using rays and objects, right? They are not just trying to do this ray and object intersection. They are trying to do an n-body simulation, which is a particle and particle collision, right? So you can imagine if, let's say, you are in discrete time step, right? For time 0, it could be here. For time 1, it could be here. But for time 3, it could be sort of like within each other already, right? So, but it's not possible for two particles to be inside each other and something like that, right? So um what they have to do is to add this little uh like epsilon at outside. So instead of having it only detect whether it's inside each other and then sort of like bouncing each other with so much force, because it's impossible for them to be inside each other, we kind of do and we kind of simulate it in a way where if it get close enough, right, within the distance of the epsilon, right, we already allow it to do all the simulations to bounce away, right? So it might not be perfectly close to each other, perfectly touching each other before it bounces, but you know as long as it's close enough and it bounces away, or close enough inside and it bounces away, and then that will be enough to actually simulate the real world to some kind of accuracy, right? So ray tracing, I mean, if you look into data structures, and you guys study data structures as well, you'll see that there are trees, there are these objects called trees and graphs, right? And turns out that it's actually a very fast way for computers to uh, do calculations. I don't want to go too deep into it because it's sort of like something that you would definitely learn in school. But yeah, if you look at ray tracing, right, and something in particular called multicolor ray tracing, right? When one ray goes from the eyes, the gray color ray goes from the eyes to the object, we actually create a few more rays, right? Maybe could be a number between 1 and maybe 100 rays if you want to be very accurate, right? Because not every object is smooth like a mirror, right? So there are maybe multiple rays that come out of one ray that hit the object, and then those few rays actually also hit other objects and have even more rays that are bouncing off of them, right? So you can sort of like do this tree, and for every single ray you create this tree, and if let's say at the end of the day one of them hits the light source, right, then you can actually do a very simple rewinding of this tree to get to the source and find out what color and what brightness is this pixel supposed to be, right? So this is the gray arrow at the start of it is like 1 pixel, and you follow all the way through, and if it hits a light, you just do the calculation all the way backwards. And yeah, this is a very efficient data structure for inside computers, right? So yeah, looking forward, right? We want to know whether computers can ever do continuous math, right? So I've shown you like so many ways where there are problems with uh continuous math, and sorry, problems with discrete math, right? Because we have to have some kind of approximation, we cannot have smooth numbers and things like that. And there are so many ways that people have been researching on to mitigate all these problems, like dithering in audio, dithering in pictures, uh reducing the number of floating point that we can use and all that kind of things, right? So can computers ever do continuous math or not, right? I think that's one question that we have. So in the traditional sense of a computer, one way we can do it is to just keep increasing the number of floating points. So in your, I showed you 16-bit, I showed you 32-bit, right? Actually, right now, most computers, right, the phones you're using, the laptops you're using, they're all on 64-bit floating point, right? What if we move even more to 128, 256, 512, 1024 floating point numbers, right? This will actually use more power, more storage, right? But we can actually do better and better simulations, right? But if we reach a point where we can simulate the world up till the smallest possible distance between two things, right, which is Planck's length, I'm not sure you guys heard about it in physics, right? Then we actually can sort of like model the entire world already, right? If you think about it from like a more meta standpoint, right? Um, is there even a need to go even further, right? The second method that we have is using analog computers. So when you think about computers, we usually think about it in a digital manner. We use bits and bytes to represent things, right? So but right now, I think because of neural networks also, people have started moving a lot into analog computers, right? And what is good about analog computers is that they use very little power. So you use so much power to do this multiplication, this MAC operation, right? Multiply accumulate operation, for deep learning. But people are moving actually towards just using maybe a amplifier, right? Amplifier is simply a sort of like a multiplication, right? In simple terms, yeah, in the analog world. Yeah, so one way that one company has done this is that, for example, if you have Siri, Alexa, Google Home sitting in your home, right, it's actually draining a lot of power. Okay, maybe not a lot, but maybe 10 milliwatts, 5 milliwatts of power, something like that, to actually constantly be listening to you. And most of the time you're not saying hey Siri, right? Most of the time you're not saying hey Alexa. So it actually discards all these things like 95% of the time or even more, right? But it's just doing this computation and taking up power. So what they want to do is actually move it down the line, and we have something in its place called this low powered RAM chip, right? So it just does a neural network in an analog manner, which uses a lot less power, right? And it might not be as accurate as a proper like digital neural network, but it's good enough such that most of the time it's listening and it's throwing away some data, and only when you hear something that is sounds like "Hey Siri," maybe something like "Hey Silly" or something like that, right? It will move. It will turn on the secondary processor, the main processor that's working now, the higher wattage processor, and do this simulation. Sorry, not do this calculation, right? So I think in a lot of um we want to ask, like, is there a point or so, right? So I would say in computing, like we don't just serve the scientists, right? We also serve the people who are interested in entertainment. We are also serving people in healthcare. We are serving people in all kinds of manner lah, because computation is really behind a lot of things right now. So in simulations, like physics simulations and scientific studies, biological studies, I would say, of course, there's a point, right, in getting higher and higher accuracy. That's why you see in your graphics card, for example, you can only do 32-bit floating point. But if, let's say, you spend another $10,000 and you buy something that goes into the servers, right, of those physicists, right, from AMD or NVIDIA, those things actually do 64-bit floating point, 128-bit floating point, right? And it's very important for them to get this kind of accurate, this kind of precision. But if, let's say, you are a consumer, right, can you really tell the difference between the 16-bit audio and the 24-bit audio, right? Some of you who are audiophiles and you buy this kind of gear, you might be able to hear the difference, but I think for most people, not really, right? For if, let's say, you're buying a TV, you're buying 4K TV versus a 8K TV, but you're sitting, at a, like 2 meters away because you are at your house, right? Can you really tell the difference? And I think a lot of times when it comes to entertainment as well, there's also this idea that um, there is some aesthetic choice in having it in a more discretized manner, right? For example, if some of you are into film, right, 24 frames per second, right, it's actually considered more cinematic and makes people feel more comfortable, like they are viewing a film, as compared to the gaming kind of FPS, which is 60 FPS, 144 FPS or above, right? So people who watch movies, they don't want to have this kind of 60 FPS, even though the technology allows it, right? So yeah, actually that comes to the end of my presentation to share with you guys about the little quirks about discrete math. Uh, yeah, if you have any questions, do like just turn on your mic and ask me right now. And if you want to connect with me, there's my LinkedIn over there, and there's also my Instagram if you guys are interested. Also, although there's nothing much there. Yeah. Any questions?